Hey guys, good morning. Here we are in chapter 4. We're going to look at trigonometry, and today's lesson is all about angles and their measure. Let's get started. Engineers in the ancient world discovered ratios within right triangles as they learned fundamental engineering skills. The secrets and patterns necessary to understanding circles and spheres helped in the development of trigonometry. Our chapter begins that journey into trig with an introduction into angles and their measures. You might recall from geometry that an angle is determined by rotating a ray about its endpoint. The vertex is the end of the ray. The initial side is the starting position, and the terminal side is the position after the rotation. An angle that is in standard position is known when the vertex is situated at the origin on a rectangular coordinate system. One ray is going to be on the positive x-axis side. That's our initial side. And when we rotate an angle in standard position, that would be counterclockwise, and the terminal side is the ending ray. We have positive angles when the angles are counterclockwise, and we could sketch one here on our coordinate plane. And then we have negative angles when the angle of rotation is clockwise. So a positive angle would begin on the positive side of the x-axis and then rotate around to some determined amount, and that landing point from the vertex, that ending ray, that's my terminal side of the ray, that's going to be a positive angle or a positive rotation. So counterclockwise creates a positive angle. And then conversely, if we rotate clockwise, that's going to produce a negative angle. And in these situations, you can draw whichever angle you want. Let's say we went 180. Let's say this went 210 degrees. So I could label that as my angle theta and name it as 210 degrees. Where if I wanted to make a negative angle, let's say we went negative 120 degrees. That would be down here in quadrant 3, and I don't want to call it theta since we called the positive one theta. We'll call this one beta. So beta has a measurement of negative 120 degrees. A clockwise rotation produces a negative angle. So that's pretty straightforward. Two angles in standard position that have the same terminal side are going to be called coterminal angles. Same terminal side, or the same ending ray. We can find an angle that's coterminal to any given angle by either adding or subtracting one complete revolution. So let's say we had an angle beta that was 36 degrees. It would be coterminal to all of the following: 396, 756, negative 324, or negative 684, and then that list would just continue on infinitely, simply by adding 360 degrees or subtracting 360 degrees from our initial angle. So those are called coterminal angles. And we can practice a few of those. Let's say we draw theta at 220 degrees. So we go counterclockwise 180 and 40 more degrees. So we're down here somewhere in quadrant 3. This is our theta angle, and it's 220 degrees. So our coterminal angle would be the same starting position. I'm going to do that in red. And if we went this way, I could name that coterminal angle as theta prime, and it would be 220 minus 360, so that negative 140 degrees would be our coterminal angle. So they have the same terminal side. And we could write over here on our notes that theta prime can also be, let's say we added 360 to 220. So if we added 360 to 220, it could also be 580 or any other full revolution of 220 plus 360 times an integer. So any other full revolution. And we could write that symbolically. Let's say 220 plus 360 k degrees, or it could be minus k degrees as well, where k is an integer, where k belongs to the set of integers, because the set z stands for integers. So 0 and all the positive and negative whole numbers. Now let's look at reference angles and how to measure angles. A reference angle is when we're given any angle in standard position. So let's just take a wild stab and call this angle 210 degrees, since they've told us this angle is 210 degrees. We want to find the reference angle, and one way to think about a reference angle is how can you get back to the x-axis in the shortest route. So the shortest route to get back to the x-axis would be this little angle right in here. That's going to be our reference angle. And we could say that this reference angle, theta prime, would be 30 degrees because you're at 210 degrees on your terminal side and you just want to get back to the x-axis, which is 180. So that reference angle would be a 30-degree reference angle. So the quickest way back to the x-axis is the thought process here. So we've got 4 of them in this example to give this concept some practice. So 150 degrees, if we start here at the positive x-axis and spin counterclockwise, 150 degrees is going to be over here in quadrant 2. This is our initial angle, or our standard position angle, and our reference angle is how fast we can get back to the x-axis. So it's got to be an angle less than 90 degrees, an acute angle. Our reference angle is 30 degrees, since 150 and 30 makes 180. In this one, 315 degrees, starting at the positive x-axis for my initial side, and rotating around 315 degrees is going to put us over here in quadrant 4, and we want an acute angle that gets us back to the x-axis. So if our initial angle, or our positive angle, is 315 degrees, and 360 minus 315 would leave us a reference angle of 45 degrees. So we could call that theta prime is 45 degrees, since theta is 315. Then we have 2 more. This one should be negative 120. Let me fix that. There you go. So negative 120, our initial side is going to be in blue. So our initial angle is a negative angle starting on the positive x-axis, spinning in a negative fashion 120 degrees. And our reference angle is going to be the measure from the terminal side back to the x-axis. So that reference angle is going to look like 60 degrees. The reference angle, 60 degrees. Notice I don't have any positive or negative rotation on the reference angle. And then the last one, 140 degrees, starting on the positive x-axis, 140 degrees is going to be 40 degrees off of the x-axis on the left side. So the angle measurement of 140 gives me a reference angle right here, this reference angle, and our reference angle would be another 40 degrees. So we're just taking that measurement between the terminal side and the closest x-axis. Okay, so here we're looking at degrees, minutes, and seconds. This is another familiar or popular way that's used in applications, and a lot of times you'll see, if you ever were in the Navy or the Air Force and were flying a plane or steering some kind of a sea vessel, you would hear about degrees, minutes, and seconds. We can write decimal degrees in terms of smaller units, and those are the minutes and the seconds. So degree is my mark for degrees, 1 prime mark is our mark for minutes, and a double prime is our mark for seconds. So you can tell that 360 degrees is one entire revolution. 1 minute is going to equal 1 degree is going to equal 60 minutes. And 1 minute is 60 seconds, or 1 degree would have 3,600 seconds. Since there's 60 minutes in an hour and 60 seconds in a minute, we have 3,600 seconds in a degree. So to use those relationships, this can be a little tricky at first if you're not familiar with it. We want to convert 36 degrees, 25 minutes, 18 seconds to decimal degrees. So you're going to need to grab your calculator, and right away we know we've got to convert everything to degrees. So I've already got 36 degrees, that's taken care of. But we have 25 minutes. So if we use the dimensional analysis, 25 minutes can be converted to, there are 60 in 1 minute, there are 60 from the table below, right here. In 1 degree, there are 60 minutes. 1 degree, there are 60 minutes. So we could multiply, doing this wrong, back the bus up. Thinking and talking and writing all at the same time. 25 divided by 60 would be the portion of a degree, since there is 1 degree has 60 minutes, and we've got 25 minutes, so we've got 25/60th of a degree. And then 18 seconds, there are 3,600 seconds, so we've got 18 out of 3,600 seconds to produce that portion of a degree. So it's the part to the whole, the part to the whole. And we said there was 1 degree had 3,600 seconds. So we're converting that portion. Now, with our calculator, let's grab that. 25 divided by 60 is going to give us 0.416 repeating. So we got 36 degrees plus 0.416 repeating degrees, and then 18 out of 3,600, 18 divided by 3,600 seconds is another 0.005 a degree. So if we add these up, we'll find that 36 degrees, 25 minutes, 18 seconds is roughly 36.4217 degrees. This is called decimal degrees. This is called degrees, minutes, and seconds. Okay, if you want, you can turn off your video and try this one on your own. Oh no, maybe I should do this one with you because it's a little different. This one we're going to convert a decimal degree back to degrees, minutes, seconds. So you can tell we've already got 42 degrees, but we've also got 0.575 of a degree. 575 of a degree, so a little more than half of a degree. And we need to cancel the degrees. So what we said earlier was that there is 1 degree has 60 minutes. There's 60 minutes in a single degree. And you can tell using dimensional analysis that the degrees are going to cancel. So with our calculator, if you multiply 0.575 times 60, that's going to give us roughly the portion that is the minutes. So with our calculator, 0.575 times 60 is giving us 34.5 minutes. So we have 34.5 minutes, but we just want the degrees as a whole number, so that's 42, and we want the minutes as a whole number, that's 34. So how do we find seconds? We're going to take this part right here, that half of a minute. So we have half of a minute, and we know that in 1 minute there are 60 seconds. So using dimensional analysis, the minutes cancel away, and 5 times 60, or a half times 60, gives us 30 seconds. So our units are seconds here. So converting 42.575 degrees is 42 degrees, 34 minutes, and 30 seconds. So we got 34 minutes, 30 seconds in this initial 42 degrees. So we converted the 575, put the remainder, converted that remainder to seconds, and we have converted decimal degrees to degrees, minutes, and seconds. All right, next we're going on to look at what a radian is. Now, a radian is another way to measure angles. And in the late 1800s, mathematicians began to see a need for this other unit of measure because they needed angle measurements that canceled out. This type of measure is also needed in calculus to help us simplify certain mathematical and physical formulas. Super important, radians do not have a unit. A complete circular revolution is 2 pi radians, 2 pi radians, and 1 radian is about 57.296 degrees. You can see that on our calculator. If 180 degrees and pi radians are compared to each other, the remainder is 57.2958 degrees. And if you think about dimensional analysis, 180 degrees compared to 1 half of a revolution, which is pi, or comparing 360 degrees, 1 complete revolution to 1 complete revolution, my answer is going to end up 57.296 degrees because radians have no unit on them. So what does that look like on a circle? Well, the definition of a radian is based on the concept of a unit circle. And when I say unit, I mean that from the center out to the edge, that's 1 unit, whether it's 1 mile, 1 foot, 1 centimeter, 1 millimeter, 1 yard. A circle whose radius is 1. If we measure off from the center, the radian measure of the angle, this measurement in here, is going to be roughly 57.296 degrees. 1 radian is about 57 degrees. So if you thought about it, 2 pi radians is 6.28 radians, and that means you can get 6, 1, 2, 3, 4, 5, 6 radians, and this little piece in here is 0.28 of a radian. 1, 2, 3, 4, 5, 6 that you could get around that unit circle, 6.28. So 1 revolution is 2 pi radians, which is 360 degrees, and 180 degrees is 1 pi radians, that's halfway across the circle. That's 180 degrees. We use a central angle for the unit circle, which was what was shown in that previous picture. The vertex is at the center. 1 radian is the measure of the central angle, which subtends or intercepts an arc, and that's what the drawing was showing. So the central angle, this is 1 radian, this is 1 unit, this is 1 unit. This measurement, this arc from here to here, if you had a piece of string, that string is the same measurement as this radius or this radius. So this angle here is 1 radian. The circumference of any circle is 2 pi r, where r is the radius. So the circumference of a unit circle, where r, something's missing right here, is the radius. So the circumference of the unit circle, where r equals 1, is 2 pi times 1. Therefore, the angle representing 1 complete revolution of the circle measures 2 pi radians. If theta is the central angle in the circle, and theta is measured in radians, then the length S of the intercepted arc is given by S equals r theta. So from here to here is going to be called the arc length, or S. In this example, we're going to look at some common radian measurements. So 1/4 of a pi radian in a negative direction. Starting here on the positive x-axis, if we went all the way over here, this would be an entire pi, because pi is 180. And this would be half of a pi at 90. So 1/4 of a pi in a negative direction would be negative 45 degrees that way. Negative pi over 4. A half of a pi would be 90 degrees, so that would be 90 degrees. In a counterclockwise measure, this is pi over 2 radians. And then pi radians would terminate on the opposite side of the x-axis. That would be 180 degrees. So this is a measure of pi radians. When we want to convert between angle measurement and degrees, from degrees to radians, you would want to multiply by pi and divide by 180. So we would multiply all of our degrees by the fraction, or the relationship, that pi is the same thing as 180. These are equal to each other. So we can use that as a multiplier. And if you want to convert radians back to degrees, we just do the opposite. Multiply our radian measurement by 180 and divide it by pi, because we want the radian measurement to cancel. Okay, so whatever you want to keep is the relationship that's on the numerator. If I want to keep radians, I put pi in the top. If I want to go back, keep degrees, I'm going to put degrees in the top. Here's about 6 examples we can try. So convert each angle from radians to degrees, or from degrees to radians. So we have a radian measurement here, and we want to convert it to a degree. So I want to keep 180 degrees in my numerator and divide it by pi. You see how the radian measurement is going to go away? When the pi's cancel, 7 times 180 divided by 6 is going to be 210 degrees. And here, same thing. I want to keep degrees and get rid of the radian measurement. So the radians will cancel. -2 times 180 divided by 3 will give us -120 degrees. So we're converting from radian to degree. And then here's the last one for you to try. And I get -96 degrees. So this is going from a radian to a degree. The next three, we're going to go the other way. So we have degree measurements, and we want a radian measurement, and a radian would be the relationship of pi is equivalent to 180. We can cancel the degrees, they'll go away, and 135 pi divided by 180 can be simplified to 3 pi over 4. Since, let's see what goes into those evenly, because 45 divides 135 3 times, and 45 divides 180 4 times. On letter E, same thing. I want to keep the radian and get rid of the degree. So 320 pi divided by 180. 320 pi divided by 180. Let's see, 20? 220. We can divide 20 out of both of those and get -16 pi over 9. And then our last one, convert -110 to a radian measurement. So this one we can just divide out a 10 in each case, and that would give us -11 pi divided by 18. So these are radian. This is a radian measure, a radian measure, and a radian measure. And then here's a little practical one. This is our last one. How many radians is each angle of an equilateral triangle? Well, if you think back about an equilateral triangle, they're all 60 degrees. So if you think about it graphically, each one of those is a third of a wedge of a half rotation. But if you couldn't see it that way, you could multiply 60 times pi divided by 180, and that's going to give us a third of a pi. A third of a pi. The next one, the minute hand of a clock travels how many radians in 15 minutes? Oh, I didn't mean to have all of these. That was extra stuff. So in 15 minutes, that would be the minute hand of a clock travels 15 minutes down to the 3. Well, that would be 90 degrees. And 90 degrees is a pi over 2. Then number 3 should have been the 10-minute question. So my slide's a little off here. In the 10-minute question, let's see, I'm going to move this down here. So the 10 minutes would be pi over 3, because that's going to be 10 minutes. It's going to go to the 2. We got 1, 2, 3. So that would be 60 degrees, or pi over 3. And then in the 5-minute question, that would be just to the 1. So if we have 1, 2, 3, that's going to be pi over 6, or 30 degrees. So this is in 5 minutes, and this is in 10 minutes, and this is in 15 minutes. And then our last example, what's the measure of theta In radians, well, we have, well, I'm really on your notes. You have a different question here. We have two different questions. Something's missing. Okay, I have that fixed. I went back and repositioned all of these questions. In 15 minutes, that's a quarter of a revolution. We said that was pi over 2. In 10 minutes, we're going to do 2/3 of a quarter revolution. And a quarter revolution is pi over 2. So we've gone pi over 3 radians. And then the hand travels in 5 minutes, 1/3 of that quarter revolution, or pi over 6. And then our last two examples, what's the measure of theta in radians if x is 45 degrees? So this measure is 45 degrees, which makes this entire thing, we can think of it this way, 45 degrees is pi over 4, since you have pi divided by 180, so that's a quarter of a pi. And all the way around is 2 pi, which could be converted into a fraction with a 4 for the denominator, so 8 pi over 4. If the entire way around is 8 pi over 4, and we've gone pi over 4, then that red angle theta would be 7 pi over 4, since 8 pi over 4 minus 1 pi over 4 is going to give us the theta measurement, 7 pi over 4. And then similarly, on example 6, all the way to the other side of the x-axis over here is 180 degrees. But 180 degrees in radians is pi. We know 180 is equivalent to pi radian. So if 5x plus x, if 6x equals pi, then x is pi over 6. So theta would be 5 times pi over 6, or 5 pi over 6. And that, my friends, is the end of Lesson 1, Chapter 4. See you next time.